Okay, so welcome to another exciting adventure of math class. This is lecture number, I believe, 7, right? We're now in the 4th week. Oh my God, 4th week already? It's crazy. And this is Math 211. And September 21st, the last day of winter. I think summer, last day of summer. That makes more sense. Last day of summer. And we're going to first recap by going over the various rules of counting that we have so far. The first one, these are the rules of counting. So we have we have the fundamental principle of counting. Can someone remind me what the fundamental principle of counting was? I forgot. What's the fundamental principle of counting? Spoiler alert, I didn't really forget. That would sound horrible, but it's just like a, pretend thing. So what is the fundamental principle of counting?
Isn't it based on the concept of multiplication?
It is based upon the concept of multiplication, right? If you have various choices sequentially, so you have choice 1. Oh, that's not how you spell choice. If you have choice 1, followed by choice 2, followed by choice 3, choice 4, choice 5, literally a sequential a sequence of events. So you make one choice, and then after that's done, then you make a second, and then you make a third, and so on. And you look at the number of ways, we'll call it N1 ways of making choice number 1, and N2 ways of making choice number 2, and so on. Then the total N is just the product of each individual number of choices. And a number of the homework questions were based upon the fundamental principle of counting. So that is the first one. And then we had permutations. Permutations were different. We had R objects chosen from N objects. Under what condition? What identifies it as being a permutation? Where what occurs? Anybody?
Isn't it where the order in which you choose things matters?
Where the order matters. Where the order matters. And we had various ways of denoting it, but at the end of the day, mathematically, we still want to have a formula for computing it. It's nice to have a symbol that denotes it, but what is the formula for the number of ways of choosing R objects from N where the order matters? Anyone recall what that formula is?
Is it n factorial over n minus r factorial?
Excellent. N factorial over n minus r factorial. And then combinations was the third big one. And for combinations, it was very similar with one difference. And what was that difference?
Order doesn't matter.
Order does not matter. And we could denote that in multiple ways. But at the end of the day, we still want to have a formula for computing it. What was the formula for the number of ways of picking R objects from N where the order does not matter?
It's the same as the previous one, except you add r factorial at the end.
On the bottom or top?
Bottom.
Excellent. It's the same as the previous one, but we also throw in an extra r factorial on the bottom. So this was the three rules of counting. There was a fourth, I guess, that we spoke about. It doesn't really have a name, but it's a number of ways that A or B can occur, is a number of ways that A can occur by itself or without worrying about whether B occurs or not, plus a number of ways that B can occur without worrying about whether A occurs, minus the number of ways that A and B can occur. I don't know if this really has a name, but it certainly is a formula that's important now. So those were what we've done in the past. Hopefully they are somewhat familiar at this point because we are going to need them as we move on. Okay, can I stop sharing on this and jump to my computer? Everyone who might be copying this has it all written down?
Yeah.
Okay. So, files. Were we on chapter 4 still? Did we finish 4? 4 was the addition rule.
We're on the princesses, I believe.
We are on chapter 5 now?
Yeah.
Okay, so the princesses. Oh yeah, the princesses. I remember. And the special people. Okay. So let me start sharing my computer now. Okay. And okay. So let's take a look. Yes, I remember this one. I remember this one. We got to this, we did this, we did the how much did we do?
We're on the page 2 on C.
Page 2 and C. Okay, so let's kind of recap it a little bit, just to remind ourselves what's going on here. Let's take a look. So 10 princesses, 30 regular girls. All right, I recall, I remember how to do this. It was, yeah, okay. So if you recall, we had this, and then we had, oh, this makes things so much easier. I think we needed a third of these, okay. So we had something like this. Let's erase this one. This one, throw them a little lower. Okay. So we drew a table, what's called a two-way table. And we had princesses. That's not how you spell it. We had princesses. And that's still not how you spell it. Okay, whatever. I'll just do it the old way. So we had princesses and we had regulars. And then we had crowns and then we had no crown. So there are 10 princesses, all of whom were crowns. So what number goes here?
10.
10, and what number goes here?
15.
0.
0, right?
Sorry.
I might have switched the P and the R and the C and the NC last time. Doesn't really make a difference. Regular girls, there's 30 in total. How many were crowns?
15.
15, and how many do not wear crowns?
15.
15, right? So if I tell you that I see someone wearing a crown, I just don't care about this. I can just remove it from, I can cover it with my finger and say, that's irrelevant for this problem because the person I'm looking at is wearing a crown. So that whole second line, ignore it. And then I see 10 and 15. I see 25. So the likelihood of being a princess is 10 out of 25 because of the 25 equally likely outcomes, 10 of them are princesses. And of the 25 equally likely outcomes, 15 of them are regulars, which means having some knowledge of, in this example, that the person's wearing a crown changes the likelihood of being a princess or a regular girl. Because if I don't have that knowledge, if I just say, what's the likelihood of being a princess or a regular girl? How many princesses are there in total? Anyone? How many princesses are there in total?
There are 10
Five.
princesses.
Sorry?
25, right?
Princesses? How many princesses are there?
10,
10. And how many regular girls are there?
30.
30. So if I say, what's the probability of being a princess? If I just see a random person, I say, is that a princess? What's the probability going to be? What's the likelihood that that person's a princess?
If we're not paying attention to crowns,
If we don't know any information other than it's a person,
it would be 10 out of 40.
10 out of 40. There's 40 people in total. 10 of them are princesses, 10 out of 40. But given the knowledge that the person's wearing a crown, it's now 10 out of 25. So the knowledge that I have changes the probabilities, and we call those conditional probabilities because it's conditioned upon some further piece of information. So how would I do it in a way that would help me see it like that? And then it says organize and display the information in another way that would indicate the information clearly to adults. Well, to adults, it's certainly the table. How would you present it in a way that fourth graders can visualize? Because this table is certainly like an adult way of looking at something. How would you present the information in a way that would help fourth graders visualize the situation? I haven't been a fourth grader in a long time, but someone tell me, if you were a fourth grader, how would you see this that might help you visualize what's going on?
With counters,
What does that mean?
like using the tokens, they're like these like little circle things that have different colors, or you could use, I guess, even the measuring blocks, the ones that are in rows of 10, and individuals are just one.
Oh,
So you
so,
can use units.
so you actually want to simulate the situation.
Yeah, just to show, I feel like that would be an interesting way to display it.
Oh,
You could
so
even
that-
draw it.
Okay, so you're talking about like physically, like give, these are the princesses, these are the people and whatnot.
Yeah,
Okay, someone said like a pie graph or maybe not. Well, it's definitely one of those two. It's a pie graph or maybe not. That's a great way to cover your bases. I love it. I don't think a pie graph would necessarily work here because how would you demonstrate the conditional aspect of it? You know, that once you
I
have,
have no idea. Maybe like, no, I don't know.
I don't know either. I probably knew at one point, but I mean, I certainly can see it in a table. So maybe with blocks or something is the best way to do it by hand. I don't know. I haven't been a fourth grader in a long time. I wouldn't ask you a question like that on a test because I care about math questions. So let's just go ahead to the next page. I don't have a good answer for that last one. I don't know. I don't know how a fourth grader would visualize it better than a table. So the princess situation requires reasoning about conditional probability. And the notation that we're going to use, and this is standard notation, is this. This vertical line can be read as given. So the probability of A given B. In other words, if I know that B has happened, B is a fact, not possible, but definite. If B has occurred, what is the probability that A will occur? This is different than just the likelihood that A occurs because knowing B might change the fact that B might occur. So let's do an example. Back to the princess example, the information is at the bottom of the page. For if one of the girls in the kingdom is selected at random, what is the probability that the person is wearing a crown given that she is a regular girl? So since the given is a regular girl, I focus all my attention on that column. Nothing else matters. The left column is irrelevant for this problem because I know that it's a regular girl. So the princesses, who cares? And what is the likelihood, given that I'm in that column, that the person's going to be wearing a crown? Well, there's 15 ways to wear a crown. There's 30 altogether. So 15 over 30. Make sense? Yes, no, maybe so?
Yes.
Yeah.
Yeah.
So let's do the next one. What is the probability that person's wearing a crown given that they are a princess?
1/1.
10 out of 10, which is 100%, right? There's 10 princesses. All 10 of them wear crowns, correct?
Yes.
Okay, so that's 100%. What's the probability that the person wearing is a princess given that they're wearing a crown?
10 out of 25.
10 out of 25. So notice, first of all, that by switching the order, you get a completely different result. How about the probability the person is a regular girl given that they are wearing a crown?
15 out of 30.
15 over, I'm sorry, I can't hear you. What?
Was it 30?
What was it, 30?
25.
25. Right? The given is wearing a crown, correct?
So
Oh.
that 25 is the princesses plus how many
Well-
crowns?
Well, no. You first look at the given. The given is wearing a crown, correct? For this problem, right?
Yes.
So all that matters is the given wearing a crown row. Nothing else matters in this problem. How many people are wearing crowns?
Yeah, 25. Okay.
25. Now, of those 25, how many are regulars?
15.
And that's why it's 15 over 25. Make sense?
Yeah.
Now, the original problem here, back a couple slides ago, was given that the person's wearing a crown, is it more likely that the person is a regular girl or is a princess? So which probabilities are we comparing to answer that question? Which probabilities do we compare to answer? Is it more likely for the person to be a princess or a regular girl in this scenario?
You're comparing the 10 out of 25 and the 15 out of 25?
Exactly. These two right there, the 10 out of 25 and the 15 out of 25. Since I know that I'm wearing a crown, I want to use that information. I'm given that I'm wearing a crown. What's more likely? It's a princess or a regular girl. In this case, it's more likely to be a regular girl because 15 over 25 versus 10 over 25. Does that make sense?
Yes.
I hope so. Let's do another one. You rolled 2 dice. Find the following probabilities. So they were very nice. They gave us the sample space. We have all 36 possible outcomes. I would like you to take a minute and write down what you think these 6 probabilities are without waiting for me to provide the answers for you. Go ahead and attempt them yourself, and then we'll go over it. Well, someone's chatting here. What are they saying? 5 sums 6 doubles. What do you mean by that? I'm sorry. There are 5 doubles with a sum of 6. I think only 1 doubles with a sum of 6.
Yeah, I was gonna say, wouldn't that be 1/36?
Well, I want you to write out what you think they are. I mean, I'm definitely willing to answer questions, but I'm not going to tell you if you're right or not. I want to give everyone the chance to kind of think about them. No problem. No problem. You guys ready?
Yes.
All right, so let's do the first one. Given that there are doubles, what is the probability that the sum is 6? What do you got?
1 out of 6.
1 out of 6. Yeah.
1 out of 6. There's 6 doubles, and only one of them adds to 6. Given the sum is 6, what is the probability that it is doubles?
I got 1 out of 5.
Excellent, 1 out of 5. Because how many ways can you get a sum of 6? 5 ways. Here they are. Those are the 5 ways to get a sum of 6, and only one of them is doubles. So 1 of 6. How about the likelihood is not conditional right now? The probability of getting doubles and a sum of 6 at the same time.
1 out of 36.
1 out of 36. Out of the 36 total equally likely outcomes, only one of them is both doubles and a sum of 6. Now, how about the probability of doubles or a sum of 6?
10 out of 36.
Awesome. Can you explain how you got that, please?
I mean, you can just count it out. There's 5, 1, 4, 2, 3, 3, 2, 4, 1, 5. And then if you go from the doubles, it's 1, 1, 2, 2. We skip 3, 3 because we counted it 4, 4, 5, 5, 6, 6.
That's certainly a viable method of doing it. You literally go through all 36 outcomes and just ask yourself which ones qualify, making sure that you only count each one once. So there's 5 sums of 6s. There are 6 doubles for a total of 5 plus 6 is 11. But one of them appeared twice. It was included in both categories. We don't want to count it twice. So we drop it once and we have 10 out of 36. How about the next one? Given a sum of 7, what is the probability of getting doubles? Given that you got a 7, when you add them together, what is the probability of getting doubles?
0.
0. It is impossible. There's no 3.5s on your dice. So if you got a sum of 7, it is impossible to get doubles. And what is the probability of doubles or a sum of 7?
12 out of 36.
12, huh? Let's take a look. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6 are your doubles. 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1 are your sums of 7s. There's no repeats in there. They are disjoints. And as a result, 12 out of 36. Of course, I can reduce these, but that's just arithmetic. These are the correct probabilities. Do we agree with them?
Yes.
All right, everyone. No, we got a chat. What do they say? And they say, oh, yes. Well, that was anticlimactic. Okay. All right. So let's clear this and move on. All right. The princess situation is an example of people sorted on 2 categorical variables. The first category is crown or no crown. The second category is princess or regular girl. Such data are often summarized in a 2-way frequency table. I've already called this a 2-way table. I've mentioned this before. Example. The Titanic carried 1,237 adult passengers, of whom 770 died. There were 86 children, of whom 49 died. Now, I watched Titanic, and I don't recall that being in the movie, so that's false advertising. But anyways, let's fill out this table. What number should go in, let's say, this box right here?
770.
770. And what number should go in this box down here?
1,237.
1,237. And what goes right here?
49.
49. And what goes right here?
86.
86. Now that's all the information that was provided with us. So can I fill out the rest of the table?
Yes,
Okay, so what's this number here?
467,
467. And what is this number here?
37,
And what is this number here?
504,
And what is this number here?
819,
And what is this number here?
1,323.
Do we all agree and it's fairly straightforward to get all those information, all those numbers?
I agree.
Anyone wondering where they came from, huh?
I agree.
Okay, that's good. Anyone else agree, disagree, adamantly agree, or adamantly disagree, or refuse to accept? Or agree, okay. All right, so we have our table. So suppose you pick a passenger at random. Find these probabilities. So what I'm gonna do is I'm gonna say adult child survived, died, okay. So I'm gonna come down here and do adult child survived and died, just so we have it handy. But go ahead, please, and answer as best you can those 5 probabilities. Oh, excuse me. So someone tell me, please, the first one, what is the probability that someone survived?
4 over 1323.
Awesome. There's 1323 people in total, 504 of which survived. I don't care adult, child. I just care about how many survived. Nothing matters, but this total number here, 504 out of 1323 survived. How about the probability that someone survived and was a child?
$37 out of 1323.
Excellent, 37 out of 1323. The same 1,323 people, 37 of them happen to be survivor, children who survived. Next, probability that someone survived or was a child.
553 over 1323.
Awesome. Can you tell me how you got that?
I added the total of those who survived along with the ones that what's it called? I did do my math. Sorry.
We add the total of those who survived with what?
With the children that survived.
The children that survived. So like these two?
I thought it was with the children that died.
Well, that's what I'm asking. Which numbers constitute survived or child?
Oh, I calculated wrong. I calculated with the 49 instead of 37.
So survived will be these two numbers.
Yeah.
Child will be these two numbers. But we don't want to double count. If we do them separately, which one do we count twice?
Children that survived would count twice.
We count the children that survived twice. So if we're going to use the 504 and the 86, we had to subtract 37 because we double counted it. Does that make sense?
Yeah.
I hope so. All right. Now, what's the probability that someone was a child given that they survived?
37 out of 504.
Excellent. Of the 504 that survived, 37 of them were children. So 37 over 504, not very high. But what's the probability that someone survived given that they were a child?
37 over 86.
37 over 86, which is much higher. Not quite 50%, but much higher than the other one. A campfire song about the Titanic says, and the captain shouted, "Women and children first." What probability should be compared to test how well the captain's orders were carried out, at least with respect to children?
If the surviving children was higher than the surviving adults.
Okay. Which means, which ones are we looking at? Which probabilities matter?
The entire surviving row.
So no probabilities, just numbers like totals or
Oh,
probabilities?
let me write them down.
Okay. Oh, excuse me.
So I'd compare the surviving adults to the total adults. So 467 out of 1,237.
Okay, so
The surviving children.
so 467 out of 1,237, which means of the adults, 467 over to 1,237, that's about 38%. 38% of adults survived. Okay, and now what's the other one you want to look at?
37 over 86.
And of the 86 children, 37 survived. That's about 43%. So would you say that the captain's orders were carried out with respect to children?
Yes.
Well, if the children all
Not
went
really.
first, yeah, if the children all went first, wouldn't that be a much higher survival rate,
Yeah, it would have.
right? I would think, it should be 100% for children and less for adults. But there wasn't enough room on the raft for all the children. So, very sad. Anyways, does that make sense? At least how to compute the probabilities?
Yeah.
Yes? Okay, now. Independence. Independence can be many things out there in the world, but in probability, it means one thing and one, well, in this part of probability, it means one thing and one thing only. So let me give you an example. What is the probability if you flip a coin that it's heads? A fair coin.
50%.
50 what? 50%. So now I'm going to give you a little extra information. What is the probability if you flip a coin, you get a heads, given that it rains today?
%50, because those things aren't connected.
Exactly. It's still 50% because what does it raining today have to do with how likely it is to get a heads? They are independent. One has no effect on the other. The additional information that you have been provided with, that one of them occurred, does not change the likelihood of the other one occurring. This is what it means to be independent. So let's see what this paragraph is telling us. Sometimes knowing which category a person falls into on one variable changes your estimates of the probability that they fall into a given category on a second variable. Next paragraph, skipping ahead a few lines. On the other hand, if I want to estimate the probability that a teen is carrying a cell phone, then knowing that it's a boy or a girl effectively has no help at any way in determining the likelihoods, because gender and cell phone possession are independent variables. The probability of someone owning a cell phone, given that they're a boy, is roughly the same as the probability that someone owns a cell phone, given that they're a girl. The knowledge of gender does not affect the knowledge of whether or not they have a cell phone. When that occurs, we say that they are independent. Let's take a look at this particular example, which is a different kingdom than the original. The numbers are slightly different. You'll notice here, by the way, that there's 90 regular girls, of which how many wear a crown? How many wear a crown here?
54.
54.
Regular
And
girls?
Regular girls, right? 90 regular girls, 54 wear crowns, 36 don't. How many princesses are there?
10.
10. How many wear crowns?
6.
6, and so on, right? The two-way table is fairly obvious, correct? Yes, no, maybe so?
Yes.
Yes.
Okay. So, question. First, what proportion of princesses are wearing crowns here?
Six?
Well, 6 is not a proportion. 6 is just a total.
6 out of 10.
6 out of 10, right? 60%. Agreed?
Agree.
Yes.
Okay. What proportion of regular girls are wearing crowns?
54 to 90.
Which is how much as a percent?
60% as well.
60% as well. We agree?
Yep.
Agree.
Huh?
Agree.
Agreed, right? So, in this kingdom, princesses are no more or less likely to be wearing crowns than regular girls. which means crown wearing and type of girl are completely independent variables. If I know the person I'm looking at is wearing a crown, it does not change the likelihood of whether they're a princess or a regular girl. They are independent. So let's actually show that. Do they show that here? Hopefully they do. They don't. Let's show that here. What is the probability of being a princess given that the person is wearing a crown? What do we get in our example? For the probability, the person is a princess given that they are wearing a crown.
6 out of 60.
6 out of 60. 60 crowns. Of those 60 crowns, we have 6 princesses. And what's the probability that it is a regular girl given that they are wearing a crown?
54 out of 60.
54 out of 60. Okay, because they have to add to 100%. Now, what's straight up the probability of being a princess?
Ten out of 100.
10 out of 100. And what's straight up the probability of being a regular girl?
90 over 100.
90 over 100. As a percent, what is 6 over 60? And what is 10 over 100 as a percent?
10%.
10%. They're equal. And how about the other example? How about the regular girls? What's the probability of a regular girl giving a crown as a percent and a regular girl by itself? They're both 90%. What we see is that knowing that a crown was worn does not change the likelihood of being a princess and does not change the likelihood of being a regular person. They are independent. One does not affect the other. Does that make sense? Yes. Okay. So here's a visual display to help us notice when we have independent variables. When they are independent, the segments on a bar chart are proportional. And the segments on a relative frequency bar chart, which is proportions, are identical. So look at the one on the right. It's a little easier to see identical than proportional. 60% of princesses wear crowns, 40% do not. 60% of regular girls wear crowns, 40% do not. We see identical bar graphs, bar charts. On the left, when we do total numbers, of course, you're going to have bigger numbers in the regular girl column. There's 90 of them compared to 10 of princesses, but the proportions are the same. So we have 6-4 on the left and 54-36 on the right. It's harder to see proportions, but they are equal. Does that make sense? Questions, answers, comments, remarks, similes, allegories, metaphors? Stories, parables, fables, yarns?
Makes sense.
Okay. I'm glad you said that because I was pretty much out of synonyms and different things. I couldn't think of any other ones. So here's a bar chart for the Titanic data. Back a couple slides ago. Here's a bar chart for the Titanic data. What do you notice about the blue and red proportions on that bar graph on the left? Are they in? They're different. And the one on the left, the blue is significantly less than 50%. And on the right, it seems ballpark 50%. So because they're not equal, they are not independent. What would be a good word for not independent?
Dependent.
Dependent. So if they're not independent, then they are dependent. Now it's asking us to draw a relative frequency bar graph. So what is the relative frequency of adults who survived versus adults who died? Not the total, which is what this is, up to 1,237. But what is the relative frequency of adults who survived? 100, 200, 300, 400, 500, 6, 7, 8, 9 is 100%. So this will be my first. What am I doing? I have this now. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is my first. Okay. Okay, so someone help me. What is the relative frequency of adults who survived? How many adults survived?
467.
I'm sorry, how many?
467
Out of how many altogether?
out of 504.
504 adults altogether?
1,037.
1237. So of the 1237 adults, 467 survived, right?
Yes.
That is 38%. 10, 20, 30, about here, 38%. So if I color, is there a way to? Oh, yeah. All right. So there are the, oh, this is awesome. What they won't think of next, huh? Okay. So those are the relative frequencies for adults. Now, how many children survived?
$37 out of 86.
37 out of 86. That is 43%. 10, 20, 30, 40. It's about up here. And therefore the rest died. So are those equal?
Nope.
No, they are not. Right? Yes, no, maybe so.
Yeah.
Okay. All right. Lovely. Okay, any questions on this? No question.
So to make it proportionate, you basically graph them like using the percentages in a way.
Yes, that's exactly it.
Okay.
That's exactly it. Okay, all right. Oh, I actually don't want to clear them, but I have to. Okay, moving on. Okay, now you can use the following method to decide whether two categorical variables are independent. And this method is more general than the graphical one that we just did, because the graphical one that we just did only holds when there's two options: crown, no crown, adult, child, survive, didn't survive. But this one works no matter how many there are. So to see if two variables are independent, for each row computes the probability of A given B1, first option for B, A given B2, second option for B, A given B3, third option for B, and so on. Go across the entire row. if they're equal across all columns, no matter which row you picked, then you know that you have independence. So let me demonstrate this with an example because it's a little hard to see. If you want to write that down, of course, you have the slides, you don't have to write it down, but I'm going to demonstrate with an example exactly how to use this algorithm. So in a classic psychology experiment, preschool children were put in a room with a treat. The investigator said that he had to leave for 15 minutes, and if they did not eat the treat until he returns, they would be given a second treat, and then they can eat both. The researchers discovered later that children who waited were much more likely to be happy and successful as adults. I probably ate it. Anyways, suppose this experiment is replicated with 4-year-olds to see if there's a relationship between ability to wait and whether the child can successfully count 15 blocks. Here are the results. So there were 30 children who waited, 60 who did not wait or couldn't wait or didn't want to wait. And of the 30 who waited, 25 were able to count 15 blocks, 5 couldn't. And of the 60 who couldn't wait, 25 were able to count and 35 couldn't for those various totals. We all agree on the scenario and what's going on here?
Yes.
Okay, so let's fill out some numbers here. What's the probability that a person can or a child can count given that they couldn't wait?
$25 out of 30.
25 out of 30. Do we agree with that?
Yes.
Of the 30 who waited? Okay, 25 out of 30. And how about can't wait? Sorry, counts given that they couldn't wait.
25 out of 60.
25 out of 60. And how about can't count given that they wait?
5 out of 30.
5 out of 30. And how about can't count given that they can't wait?
35 out of 60.
35 out of 60. And the question is, are these two variables independent or not? So here's the idea. If they were truly independent, then this and this, waits or can't wait, should have no effect on whether they can count. So that these two should be exactly the same. Or they should have no effect on can't count, so that these two should be exactly the same. Are they?
They're not.
They're not the same. And that's all you need to know. So 25 over 30, which is this over this, is not equal to 25 over 60. Or 5 over 30 is not equal to 35 over 60. In other words, pick whichever row you want. It makes no difference which row you use. And that, so if you use the first row, 25 over 30 and 25 over 60 should be the same, but they're not. Or if you use the second row, 5 over 30 and 35 over 60 aren't the same. Either way, you get the same results, that these are not independent, that one has an effect on the other. So let's go back and reread that algorithm to see if two categorical variables are independent. In this case, one is this one, waits can't wait, versus counts can't count. To see if they're independent. For each row of the table, for each row, so we did 2 rows, counts and can count. For each row, compute the probability of A given B1, A given B2, and so on. In our case, weights, counts given weights, counts given can't wait. Can't count given weights, can't count given can't wait. Across the entire row. They have to be equal across all columns, no matter which row you pick. For the first row, they got to be the same. For the second row, they got to be the same. If any row they're not the same, done, not independent. So maybe you'll have 10 rows and 7 of them are the same, but 3 of them aren't. Not independent. So any row you pick, when you do that value over the total, that value of the total should get the same thing. If we go back to that princess example, here, 6 over 10, 60%. 54 over 90, 60% equal. 4 over 10, 40%. 36 over 90, 40% equal again. Okay, if they're equal for every row, then the categorical variables are independent. Does that make sense?
Yeah.
Seem reasonable? Okay. So the table gives all the accidents with injuries in the city of Los Angeles in 2013 for drivers of the given age. You have 16, 18, or over 90. There's a total of 449 accidents, of which the driver was at fault, 263, in which the driver was not at fault. And then you have the total for each age category. And the question is, are the variables fault of driver and age of driver independent? Yes or no? So someone tell me, are they independent or not? Yes or no? And why, of course. Anybody? Anybody want to help me out here?
Would it be no?
Why would it be no? Tell me the reason why.
It wouldn't be independent because okay, I went out. Okay, I lost my train of thought. Dang it.
I mean, the
Yeah.
percentages, oh, you can continue. Sorry, I was gonna try to pedal off of you, but
Go ahead. Sorry, no.
you sure? Okay, so I was looking at the 73 over 113, age of 16 drivers at fault, and the totals to see if the percentages would be similar. And they're both in the 60%-ish range, but there's a difference between a few percentages in between.
Right. So when you do 73 over 113, I get 64.6%, right? And then when I do the next one, I get 62.7%. And when I do the next one, I get 63.6%. So my first instinct is, oh, they're not the same. They must be independent. Or sorry, they must be non-independent. But then I also realize that this is just a sample. This is not the true value, whatever it is. So if I include the possibility of stabilization, are these close enough to each other that I would be surprised if they were really equal? Like if one was 2% and one was 80%, right? If one was 2% and one was 80%, and you said, oh yeah, I just haven't reached stabilization yet. After a sample size of 712, 2 and 80, those are really far apart.
Mhm.
But these are within 1% of each other, right?
Exactly, because then you can just
Right.
round off, you could just 65, 63, and then 64. So they're just within like 1% of
They're
each other.
within 1% of each other. So I would say that, the data doesn't prove one way or the other, but they're certainly close enough to each other that I wouldn't be surprised if they were independent. Does that make sense?
Yeah, so when it's close like that, if you were to give us a problem, then it's fine.
Yeah, because this is a
Okay,
sample, because it's only a sample, right? Samples are going to be approximating true values.
Mhm.
They don't always give true values, but they're going to be at least, they should be close.
Okay, cool.
And in fact, this is a big one right here. One of the differences between probability and statistics is that in statistics, we can say, are they close to being independent? In other words, given that it's a sample size, are they close enough that we can claim independence here or not? Does that make sense?
Yeah.
Okay. Now, does this seem true for these ages? Do you think your answer would change if a column for age 40 were added to the table? If I added an age 40 column, do I still think I would get the same values across the boards?
Probably not.
Probably not. I mean, young kids are a little reckless. They don't have the experience. Old people, older people, they don't have the reflexes. But someone who's 40 or so is probably safer. Okay. And would probably have a lower percent of at-fault accidents in that situation. Does that make sense? I hope it does.
Yes. Yes.
Okay.
Yeah.
All right. So here we have an example where the table gives the marginal totals, that's the totals in the margin, marginal totals, and the grand total. The grand total is 100. And we want to fill in the 4 cells so that the variables are independent. So we know the first 2 columns have to add to 80, the second one have to add to 20, the first row's got to add to 35, the second row has to add to 65. But if you just put in any numbers you want, chances are you're not going to have independence. So I would like to fill in the 4 cells so that we do have independence. And we can get this done. We got 6 minutes. We can finish the page and done with chapter 5. Be awesome. So let's fill in the 4 cells so that we have independence.
Could it be any number that adds up to 35? The total?
Well, give me some numbers and we'll just check if that works
Okay.
or not.
What
Some
about
numbers.
28?
For 28 for which one?
Drink sport. Drink.
Okay, so here 28.
Yeah, and
And
7.
that must be 7. This for therefore and this must be 13, and therefore this must be 52. So let's take a look if we have independence. What's 28 over 80?
%.
And what's 7 over 20?
35.
Okay, so tell me how you got that, because if that was just a guess, that was crazy lucky.
No, yeah, I was. I wanted to get the 35.
So you just randomly picked 28.
Yeah.
Crazy.
Then I put it.
Crazy, because that's the only way it would work, I think. Trying to think if there's another option here. Because if you raise 28, if you make it a higher number, that percent goes up, but then you have to lower 7, so that percent goes down. So this is the only number where they would be equal, 35%. All right, if I did 29 out of the 80, and therefore 6 out of 35, the numbers wouldn't work anymore. Someone said, isn't it because it's factors of 7? I don't think that's I mean, that might be coincidental for this problem, but I don't think it's universally a factor. No pun intended. It's just, yeah, so that was just a great guess. I mean, or maybe it wasn't. Maybe there was a lot of thought going on behind the scenes. But at the end of the day, you can do it mathematically. You can do it that way. I can say, I can do the following. We're not going to do it this way, but just imagine this. I'll call this X. I'll call this Y. I'm going to call this W. And I'm going to call this Z. And I don't know X, W, Y, or Z. I want to find them. So what do I know about them? Well, I know X plus Y has to equal 80. I know that. And I know W plus Z has to equal 20. I know that. And I know X plus W has to equal 35. I know that. And I know Y plus Z has to equal 65. I know that. Normally, if there's 4 unknowns and 4 equations, then you're good to go. But unfortunately, one of these is redundant, which we're not going to get into why, but it is. However, I also have that X over 80 has to be the same ratio as W over 20. And a redundant one, Y over 80 must be the same as Z over 20. So I have these 6 equations. And if I were to go ahead and solve these 6 equations, this is the only solution that would work. But for you guys, it's purely plug and chug. You try it and you just try to find one that works. Okay. Now, do you think that these 2 variables would actually be independent in a sample of 100 high school students? If those high school students, do I think they would still be independent, or would I think that playing a sport and drinking sports drink would have more of a connection?
It would have more of a connection.
I think so too. I know that when I play sports, you know, get a Gatorade or one of those power drinks or something. I'm certainly more, you know, likely to do so. But again, I stick to the math questions. I don't really like questions like this. Okay, so at this point, we finished we finished chapter 5. So let's remind ourselves of the chronology here. We have a quiz today on, which I'll put up in like 5 minutes, on chapter 3. And then we have a quiz next weekend on chapter 4. And because we finished chapter 5 today, the homework for this will be due next Tuesday. And you guys want to have a, we have to have a certain number of quizzes. So, because it's a big portion of your grade. So when do we plan on having a quiz on this chapter? Next Tuesday to Thursday, much like we had a Tuesday to Thursday one today and a Thursday to Tuesday one. So is that okay with everyone?
Yes.
Okay. Sounds good. All right then. Well then, I will see you all on Thursday. And make sure to get the quiz that I'm about to put up in before Thursday. And also, of course, I'll put up the homework solutions as well for you to look over in case you are sufficiently interested. Okay? So I will catch you all later. Peace out.
Thank
you.
See you.
Thank you, Professor.
Professor, I have a
Professor.
question.
Yeah.
So I checked my Canvas page today and it said I was missing page 1 of quiz 1, but I double checked.
Oh, you're
and it's
Elizabeth,
there.
right?
Yeah.
Yeah. So I know you sent it to me, so I'll update it. I just haven't had a chance yet.
Okay, thank you.
No problem.
Have a
Okay, I'm gonna stop recording.